Okay, so we're going to do a two-dimensional kinematics problem now. We've done a couple one-dimensional ones, and I think it's time we beef it up a little bit and go with a two-dimensional kinematics problem. Now, the cool and kind of the big picture idea with two-dimensional kinematics is that it's really just two one-dimensional kinematic problems. So let's go ahead and take a look at this one. A tennis player wins a match at Arthur Ashe Stadium and hits a ball into the stands at 30 meters per second at an angle 45 degrees above the horizontal. On its way down, the ball is caught by a spectator 10 meters above the point where the ball was hit. Calculate the time it takes for the ball to reach them and the magnitude and direction of the ball's velocity at impact. Okay, well, let's do part A. So we know that initially it's hit with velocity of 30 meters per second, an angle 45 degrees from the horizontal. And I'm sure you're all very happy that I'm not the one drawing the picture, because that'd be awful. The other thing I put down is the kinematic equations here. I know they're in terms of x, but you can also think of replacing your x with y's, and you get the same thing. Okay, so let's go ahead and make a list, I guess, over here. X initial, X final, V initial X, V final X, acceleration X, and time. And then we're going to do the exact same thing. So this is your X motion. Then over here we'll do Y motion. It'll be the same thing. We're just using different variables. It's really important we keep track of all this stuff. It kind of did it for us, but just for the heck of it, let's make sure that we know that right here is our origin. Right there is our origin. Okay, so let's go ahead and list what we know. If that's our origin, then X initial is 0, Y initial is 0. We don't know how far it goes, but we know that, so this we don't know, but we know that the initial velocity in the X direction, well, if we look over here, right, this is our X component, this is our Y component, and then this is the magnitude. And that velocity at an angle is really just a vector in the X direction and a vector in the Y direction. So using some right triangle trig, right, we know that this is V initial cosine theta. Now, also in the X direction, we know there's no acceleration in the X direction. So if you have no acceleration, acceleration is your change in velocity. And if there's no change, then V final is the exact same thing as V initial for X, because there's no acceleration in the X direction. There's gravity. That's something that's accelerating our tennis ball. But that's in the Y direction, not the X direction. And then as for time, that's really what we're looking for. And time's the same for X and Y, so we can use either one to find it. Y final, we do know that. We know the person's 10 meters above. V initial and the Y, again, Y is opposite, so ka, it should be an H, toa, remember, SOHCAHTOA, right triangle trig. Opposite is sine, so V initial sine of theta. Now we can't say V initial sine of theta is V final because we do have a force acting on it, gravity. And again, we don't know time. Okay, well, let's look at this. Is there any one of these where we can go and solve for time? Well, let's look at our kinematic equations. We have, I'll go ahead and label this 1, 2, 3, 4. And don't get too tripped up by the x's because we can easily replace those with y's. Not a huge deal. Okay? Well, let's see. Let's look at number 4. Except, again, instead of x, let's think of it as y equals y naught, which is y initial, plus velocity initial in the y direction times time, plus 1/2 at squared. This is y final. Well, this we know is 0. So y final equals v naught sine theta times time, right? Because v naught in the x direction is right here. And then acceleration's g, so I'm just going to say minus 4.9 t squared. Okay, and we know y final is 10. I'll go ahead and replace, you know what, no, I'm going to do this. Plus 1/2 gt squared. I want to keep everything as variables, just as an important lesson. So how are we going to do this? Well, this is a quadratic, so we can say 1/2 gt squared plus the initial sine theta times t minus y final is equal to 0. And if you remember the quadratic, t is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. It's a little weird here, but we can plug in variables now, I suppose, and we'll get minus 4.9 t squared plus, I have to use the ti here, v initial was 30, so 30 sine of 45, which is just 25.527 t, minus 10 equals 0. Okay, so we would just plug this in. This is our A, this is our B, this is our C. You could plug it into there. I programmed the quadratic equation into my TI, which I can show you guys later if that's something you want. But I don't feel like plugging these numbers in, so I'm going to be lazy. And I got t equals 4.78 for our time. So quick adjustment, maybe you guys caught this if you're working around, but I had my degree or my calculator in radians because I was doing calculus earlier, and this is obviously not what we want. That changes our B to be 21.213 because when I worked through it, that time didn't make sense. Okay, so let's try this one more time. Negative 4.9, 21.213, negative 10. And now we get a time of 3.79 seconds. There we go. So part A answered. For the ball to go from there to there, it takes a total of 10 seconds. Now it wants to know the magnitude of the velocity here. So we have our velocity vector, and that's composed of Vy, Vx, and that's our V. Well, we know V final in the x direction, right? that doesn't change. But with y, this is a little trickier because we have acceleration. But now that we know time, we can add... This is no longer a mystery, right? We just solved for it. It was 3.79. And nicely, we can see that velocity final is equal to v initial plus acceleration times time, and we just found time, so works perfectly. V equals v naught plus at, which is going to be v initial v initial sine theta, right? That's our y component, plus g times t, which we just solved for. So let's go ahead and plug that in. V naught, so 30 sine of 45 minus 9.81 times our time of 3.79. So v sub y is negative 15.9667 meters per second. And that makes sense that it's negative. It's an awful box, but we'll go with it. We're letting up be positive, right? And we can see that from our up and right. We can see that from our coordinate axes we set up there. Well, now we have the x, so we know this, and this never changed. So if we want the magnitude, that's just the square root of vx squared plus vy squared. So the square root of that thing we just found squared plus 30 cosine 45 squared. I'm sorry, that shouldn't be a y, that should just be v. I get about 26.55 meters per second. So hopefully that makes sense. We started by, well, they drew the picture for us, thankfully, but then we looked at the x direction and the y direction. And to find time, the way we did it with this is and I should mention this really quick, especially if you're going to have an exam on this. That's not what I wanted. This particular equation, this quadratic, all this guy, I know that's not pretty, but it's fine. This one is used a lot, very often actually, and really the only trick here is you had to remember your quadratic equation for this one. Once you got time, you had to use the first one to find our velocity in the y direction, making note of the fact that when acceleration is 0, these two are going to be equal. Here acceleration is not 0, so these two not equal. So we had to find v final there. And then once we do that, finding the